Testing, can you hear me? Testing, can you hear me? Okay, this video is public now. So I'm going to be learning surface integrals again. I did not complete that chapter. So I will continue that. Going to surface integrals. Okay, let it load properly. Recall that to calculate a scalar or vector line integral over curve C, we need first to parameterize C. In a similar way, to calculate the surface integral over C, we need to parameterize S. That is, we need a working concept of a parameterized surface. And now, instead of just t, they're using two variables to define r. So r uv, cos u, sin uv, this defines a cylinder. If you keep v constant, the cos u and sin u will make a circle. And if you keep if you keep u constant, v will just make a straight line in the z-axis. So we just have a cylinder. Yeah. So cos u, sin u makes a circle. Changing u gives this for different values of v. And then for different values of u, we just have a straight line when we check v. So we get a cylinder in the end. And over here, discuss parameterization of various surfaces, but two important types of surfaces need a separate discussion: spheres and graphs of two variable functions. Parameterize a sphere, it is easier to use spherical coordinates. The sphere of radius rho centered at the origin is given by the parameterization r phi theta, rho cos theta sine phi, rho sine theta sine phi, rho cos phi. Okay. Finally, to parameterize the graph of a two-variable function, we need to let z is equal to fxy be a function of two variables. The simplest parameterization of the graph of f is rxy. In xy, f of x, rxy is xy and f of x of y. Where x and y vary over the domain of f. For example, the graph of x square y can be parameterized like this. Let's now generalize the notions of smoothness and regularity to a parametric surface. Recall that a curve parameterization Rt from A to B is regular if the derivative is not zero. for all t in AB. Uh, okay. For a curve, this condition ensures that the image of R really is a curve and not just a point. The image of R. Okay, what do they mean by the image of R? I forgot. The image of this parameterization is, for example, consider the curve parameterization RT12. The image of this parameterization is simply 0.12, which is not a curve. Notice that also the derivative of RT is equal to 0. The fact that the derivative is the 0 vector indicates we are not actually looking at a curve. Analogously, we would like a notion of regularity for surfaces so that a surface parameterization really does trace out a surface. To motivate the definition of regularity of a surface parameterization, consider parameterization RUB 0 cos V1. Although this parameterization appears to be a parameterization of a surface, notice that the image is actually a line. How could we avoid parameterization such as this? Parameterization that do not give an actual surface. Notice that the derivative with respect to u is 0, 0, 0, and with respect to v it's 0 minus sine in 0. Its corresponding cross product is 0. The analog of this condition, of the condition derivative of r is equal to 0 is that the cross product is not 0 for any point ub. I think this is supposed to be not equal to 0. Uh, Parameterization RUV is a regular parameterization if the cross product is not 0 for any point UV in the parameter domain. If parameterization R is regular, then the image of R is a two-dimensional object as a surface should be. Throughout this chapter, parameterization RUV are assumed to be regular. Recall that the curve parameterization RT is smooth if the derivative of R is continuous and the derivative of R is not 0 for all t. Informally, a curve parameterization is smooth if the resulting curve has no sharp corners. The definition of a smooth curve parameterization is similar. Informally, a surface parameterization is smooth if the resulting surface has no sharp corners. Surface parameterization RUV is smooth if vector RU cross product RV is not zero for any choice U and V in the parameter domain. A surface may also be piecewise smooth if it has smooth faces, but also has locations where the directional derivatives do not exist. Okay, this is smooth and this is not smooth because piecewise smooth. Okay, this over here is piecewise smooth because it has directional derivatives which do not exist, right, on the corners. The sharpness of the corners ensures that directional derivatives do not exist at those locations. Our goal is to define a surface integral, and as a first step, we examine how to parameterize a surface. The second step is to define the surface area of a parametric surface. The notation needed to develop this definition is used throughout the rest of this chapter. Let S be a surface with parameterization RUV over some parameter domain D. We assume here that RUV is continuously differentiable. Assume for sake of simplicity that D is a rectangle. Divide D into sub-rectangles Dij, horizontal with Du and vertical with Dv. Okay, so V is span from here to here, U is spanning from here to here, and Dij is this. They're dividing the UV grid into Dij, and then this corresponds to Sij. Okay, so the values of V over here corresponds to values in Sij here. Divide rectangle D into subrectangles Dij with horizontal width delta U, vertical width delta V. Suppose that I ranges from 1 to M and J ranges from 1 to N, so that D is subdivided into M n rectangles. This division of D into subrectangles gives a corresponding division of S into S pieces Sij. Choose point Bij in each piece. Si. Point Pij corresponds to point UIVJ in the parameter domain. Point Bij corresponds to point UIVI in this domain. Okay. Point Bij could be anywhere in Sij, right? Point UIVJ can be anywhere within this subrectangle. Point Bij corresponds to that point, to the point in this domain, right? Now that we can form a grid with lines that are parallel to the u-axis and the v-axis and the uv plane. These grid lines correspond to a set of grid curves on surface S that is parameterized by RUV. Without loss of generality, we assume that Pij is located at the corner of the two grid curves. Okay, so then, okay, so we're assuming UIVJ is in the corner, right? If we think of R as a mapping from the UV plane to R cube, the grid curves are the image of grid lines under R. To be precise, consider grid lines that go through point UIVJ. Okay. So this grid line and then this grid line. One line is given by x is equal to UI. The UI keeping V constant. So V is constant. So sorry. V is constant and it's the U that changes, right? So it's referring to this grid line over here. And the image of this grid line is this, right? This grid line. Similarly, for this grid line, where U is constant but V changes, the image is here. The first grid line, the horizontal component is held constant, yielding a vertical line through UIVJ. In the second grid line, the vertical component is held constant, yielding a horizontal line through UIVJ. The corresponding grid curves are RUIV and RUVJ, and these curves intersect at a point Pij. Now consider the vectors that are tangent to these grid curves. For grid curve RUIV, the tangent vector Pij is tangent V. So, the derivative of R with respect to V. Right. So the derivative of R with respect to V. And then for the grid curve RUVJ, we have derivative of R with respect to U. If vector n is the cross product, these two tangents, cross product exists and is not zero, then the tangent plane at Pi exists. If piece Sij is small enough, then the tangent plane at Pi j is a good approximation of the piece Sij. We have V naught, U naught, we have U naught, V naught, and then the point corresponding is over here. And we have TU, then TV. And then this is the normal curve. The tangent plane at Pij contains vectors TU Pij and TV Pij. Therefore, the parallelogram spanned by TU and TV is the tangent plane. Since the original rectangle in the UV plane corresponding to Sij has width UV and length delta V, has width delta U and length delta V, delta U, delta V. Parallelogram that we use to approximate Sij is the parallelogram spanned by delta U TU and delta V TV. In other words, we scale the tangent vectors by constant delta V and delta U to match the scale of the original division of the rectangles in the parameter domain. Shouldn't the tangent be unit vectors first and then we scale it? Constant U V to match the scale of the original division of the rectangles in the parameter domain. I don't understand. Why is it not a unit tangent vector? In other words, we scale tangent vectors by constant delta U and delta V to match the scale of the original division of the rectangles in the parameter domain. Therefore, the area of the parallelogram used to approximate the area of Sij is delta U TU cross product delta V TV. It's still not clear to me why it's not a unit vector. This proof would have made sense if they defined TV as a unit vector, like the derivative of RV divided by the length of this vector. So I get it, this vector RV is like this over here. This vector RU is like this over here. If they made it a unit vector, it would make sense. Weighting point pi over all pieces Sij, the previous approximation leads to the following definition of the surface area of the parametric surface. If the derivation is not clear to me, this part is not clear to me. Why is it not unit vector and a normal tangent vector? Why is it the whole tangent and not the unit tangent? Is it because for very tiny Sij, actually, never mind. Calculate the lateral surface area of the right circular cone with height h and radius r. Going up, I want to remember how they defined a circle. They defined a circular cone, right? The parabola. U cos V, U sin V, U. So example 6.62. If I have R U V, X is this, Y is this for different values of V. And then radius R, right? Going from 0 all the way till R. So if we so at a particular, let's say we fix U to like R half, then we have a cone R half, then we have a cone scaled by this value, right? And then like if it's all the way till R, then we have it like scaled it to a much bigger value. And then after this, it becomes much bigger. Yeah. Now, and then this will vary. This will be U, right? Then this will define a cone. So from 0 all the way till R. Now they want cross product. Uh, Cost P will remain the same. This will remain the same. This will be 1. Now if we do it with respect to B, uh, derivative of sine is cos. Derivative of cos is minus sine. Then 0, right? And then the cos product of these two. Cos sine 1 This part is cos v. This minus this plus this minus this, but then minus the whole thing. This minus this. This minus this. So u cos square v, this minus this, plus u sine square v. Okay, and then that's just u. Sine square and cos square, they give 1. This is the cross product. And then we have the length of this, right? So u cos square v plus u square sine square v plus u square. From 0 to r, and then from 0 to 2 pi. These two will just make 1. So this root 2 will go out. Then this is I feel like this is wrong. This is constant, right? 0 to 2 pi. Hey, the height h, where is that? Height h and radius r. Zero, zero all the way till r. kv 0 to h. They define a third variable k, Let alpha be the angle that is swept out by starting at the positive z-axis and ending at the cone. Let k equal to tan alpha, the height value v, the radius of the circle found by intersecting the cone with the plane is c is equal to v, which is kv. Therefore, the parameterization of the curve is, wait, u cos v and u sin v, that I understand. But don't we need another parameterization k going from 0 to h? Or we multiply h over r over here. R square over 2 h over r. I don't know what I'm getting. Where am I getting it wrong? Let's see what they're doing. Is the derivative correct? So if they defined it like this, is my derivative correct? This cos sine 1, cos sine 1, and a sine cos 0. Then they have kv root 1 plus k square. How? We derivated with respect to u. Okay, how about this? Let k equals h over r. So now we have k, uk, and with respect to u, this will be k. This will be, oh, k is already used here. L, 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 this minus this minus this and this. Okay. L square U square. Sine square cos square is 1, so we are left with L square U square plus U square. Then we are left with U square plus times L square plus 1. L square plus 1. L L L L L square over 2. This is a constant, right? And then L is H over R. Hold on. H square over R square. H square plus R square over R square. H R cube over. But this is wrong. Pi R root H square plus R square. So where am I getting this wrong? U changes from 0 to R. Oh, U changes from 0 to R. 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 From 0 to R. R square. r square. And if we take the r out, we are left with r. So my derivation is correct. Lateral surface area of the cone is pi r root h square plus r square. Show that the surface area of the sphere is of the sphere x square plus y square plus c square is r square. Let me think. 6.63. Okay, they said x square plus y square plus z square is r square. And they said that the sphere is defined like this, like from 0 to 2 pi, then phi goes from 0 to pi. Radius is phi. Cos theta sine phi. Sine theta sine phi. Cos phi. And we they want this, right? But is it the same? It's the same, right? Well, in this case, it would be a if I do this. Derivative with respect to phi becomes r cos theta. Sine becomes cos. Sine become, oh my god. Derivative of the first times the second. Plus the first times the derivative of the second. No, I got this wrong. It's only with respect to phi, right? Only this part. There. Derivative of cos is minus sine. And then we have cos. And then with respect to theta, this power 1 is 0, right? I think that should make things easier. Yeah, actually, I think it's better since they're already besides each other. So for I, we have these three: I, J, K, I, J, K, I. Actually, no, I'll just. So R cos theta cos phi minus sine. I should just write C and S. C, C phi. S theta cos phi minus R sine phi 0. R cos sine phi sine theta sine phi. S minus this. Minus will make it positive. So we have R square this times this. This is a minus. This is also a minus, right? R square these two multiplied minus these two. Theta and then cos theta. Cos phi, I mean. Okay. Oh my god. Cos square. Cos phi sine phi. Cos phi sine phi. But if it has cos phi sine phi, because this will be One right. No, no, actually, this square plus this square plus this square. Cos square sine 4, sine 4, sine 2, cos 2, sine 2. I'm wondering if I can do a nicely split them somehow. I don't think I can. I can take sine phi out. I have let's say cos phi. With respect to phi, we have cos. Derivative of sine is cos. Derivative of sine is minus cos. Sorry, derivative of sine is cos here. That's correct. Theta minus sine, cos, and 0. Cos, cos, sine, cos, sine, 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 cos, sine, and 0. We have this times this r square, sine square cos, r square. Okay, yeah, yeah. So this times this times this is 0. Then we do this times this becomes positive. This times this minus this times this. Actually, no, since it's the middle one, it's minus this times this plus this times this. But if it's a plus, then this should be positive. R square, sine, Hold on. I think this is wrong. Square is over here. And then we have r square, cos theta, cos phi, cos theta, sine phi. This times this. We end up with cos square theta, right? Minus this times this. Then with sine square theta, but cos square and sine square, they become 1. So this square, cos square, sine square phi. This square, and then sine phi 4. And then this square. Took the r out. Sure. Sine. Okay, let's think about it now. Because cos here, sine here. Can add them and this will become 1. Uh, then we integrate this. 0 to 2 pi and then 0 to pi, right? We can take the r square out. Can derive it with respect to phi first. Imagine if it's a simple answer. Okay, I made a mistake. So r to the power of 4. Sine 4 cos 2. Sine 4 sine 2. Sine 4 sine 2. Sine 2 cos 2. Sine 2 cos 2. Phi phi. Oh, this is phi over here. I wrote theta. So I was on the right track. And this is 1, right? D pi d theta. Pi goes from 0 to pi. 0 to pi, let's integrate that first. Integrate. So derivative of cos is minus sine. Derivative of minus cos is sine. Minus minus cos 0. Hold on. What is cos pi again? Cos pi is negative 1, right? 0, negative 1, negative 1, minus plus 1. 0 to 2 pi. And that's an issue. Hold on. Then from 0 to pi, derivative of integral of sine is minus cos, right? Derivative of cos is minus sine. Integral of sine is cos. Yeah, that's correct. Minus 1 plus 1 gives 0. This is an issue. Minus 1 minus cos theta. So then this will become minus 1 minus 1, which will become minus 2. Pi is this is negative 1 minus minus 1 will become 2. Minus minus 1 minus 1. So 2 minus 1 is 1. But doesn't that leave us with pi 2 pi r square? How 2 though? Cos 0 is 1. How though? Uh, Derivative of sine is cos. Then we have not empty list. How do we do the evaluation thingy? Cos pi minus cos 0 gives a negative 2. But then minus all of it will give positive. Wait, hold on. Okay, I think I know the issue. So minus cos pi minus. This was the issue. Negative 1, negative 1. Now it makes sense. In addition to parameterizing surfaces given by equations or standard geometric shapes such as cones or spheres, we also parameterize surfaces of revolution. Okay, so they have r, x, theta, x, f of x cos x, and f of x sine theta. From a to b, from 0 to 2 pi. So from a to b and from 0 to 2 pi. All right. Let me, okay, I will have to go somewhere. So I will just look at this example and I will end the stream. Find the area of the surface of revolution obtained by rotating y is equal to x square. Y is equal to x square. We have this function. X square cos theta, square sine theta. Dx is this, d theta is this. Oh my god. The area of the surface of revolution is this. Right. I'll end my stream here then. And when I get time, I will continue. This chapter alone is spanning 3 streams. I don't think one chapter has taken so long. Okay, I will end the stream here then. And yeah, we'll see you guys next time. Bye.